In this video, we take up array alignment. We begin with an overview of the operation, then introduce the tools and hands-on exercises that are included in the NeuroDOT distribution. Although the MATLAB version of the NeuroDOT alignment tool is demonstrated here, the workflow and background described are relevant whether you are using the MATLAB or Python implementation of NeuroDOT or doing cloud-based processing through the Oxy website. We begin with the what and why of array alignment. Put simply, in order to process array data, NeuroDOT must be told the scalp position of the optodes. At first glance, this appears to be straightforward. Each optode has a known position in the array, so knowing the orientation of the array on the head should allow the scalp position to be determined. However, there are two complications. First, we require optode positions to be expressed in the coordinate system of the finite element mesh used for light modeling. The mesh coordinate system is derived from a structural image of the head, either a T1 scan of the subject or a normalized atlas. This likely has a different origin and orientation than the optode coordinate system, which may simply be referenced to a convenient location on the array. A second complication is that the shape of the skull affects placement. The position of the optode in the array is not necessarily the same as its position on the scalp. Typically, a mechanism is included in array design to work with irregularities, such as spring-loading the optodes. We must include these adjustments when calculating optode positions. The NeuroDOT documentation refers to this operation as array alignment. We are aligning the array and the finite element mesh by specifying their geometries in a common coordinate system. The operation is not conceptually difficult, but it requires a systematic approach. To this end, NeuroDOT provides the Alignme application. The main window of the app is shown here. Alignme provides controls for adjusting the array position, view selection, and loading images taken during the experiment that document array placement. In the center display, the array is superimposed on a finite element mesh of the head, which is used to guide alignment. Detailed usage is described in several PowerPoint tutorials included with NeuroDOT. We will introduce these later in the video. The Alignme app is just one component in array alignment. The overall workflow is summarized here. Alignment begins with documenting the array position during the experiment. This documentation may comprise photographs, measurements, fiducial markings, or any other assets that may be helpful in verifying the position of the array on the head. Next, the optode locations in the array must be specified. In NeuroDOT, this data is called a pad file. Pad files for several common optode arrays are provided in the distribution. If your array is not included, you will need to generate a pad file for it. Instructions can be found in the PowerPoint tutorial shown here. The final resource required in alignment is a finite element model of the head. In the full alignment workflow, this is constructed from a structural image of the subject. Alternatively, good results can generally be obtained using a structural atlas. This workflow is required if a subject-specific mesh cannot be generated. A standard structural atlas is included as part of the NeuroDOT distribution. Once these resources are prepared, array alignment can begin. The Alignme app is launched, and the array documentation, pad file, and head mesh are loaded. Alignment consists of incrementally repositioning the array. Coarse adjustments are done manually, using the GUI controls. Fine adjustment is done internally by the software, utilizing a process termed relaxation. Using the current coarse position as a starting point, each optode is advanced independently until it contacts the mesh. This mimics the physical mechanism used in the array to obtain good scalp contact, such as spring-loading the optodes to move radially inward. Array alignment is thus an iterative process of manual positioning followed by relaxation. After each cycle, the optode contact positions are displayed, and these are compared with the documented array placement. Once an acceptable agreement is obtained, alignment is considered complete. The optode positions are then saved to a file so the data is available to NeuroDOT for later processing. Before continuing, however, it's good practice to double-check your alignment results. A simple check is a visual inspection. You should be able to identify all optodes in your final array placement and all optodes should contact the head. In other words, no optode should be inside nor outside the mesh. A more rigorous confirmation can be obtained by including a localizer task as part of your experimental protocol. This consists of presenting a simple stimulus that results in an established pattern of cortical activation. Comparing the expected and reconstructed results provides a check not only on the accuracy of array alignment, but on your entire processing pipeline. For this reason, many experimenters include a localizer task whenever possible. Several of the NeuroDOT PowerPoint tutorials include a section on array alignment, but the recommended introduction is the standalone Alignme exercise highlighted here. This tutorial features a simplified workflow that is helpful for the first-time user. A pad file and standard head mesh included with the distribution are used. You can simply load these files, then proceed directly to practicing with the app. Additionally, rather than working with documentation of the array position, a target placement is defined, which you are asked to reproduce. Nonetheless, the tutorial follows the workflow described previously, with manual adjustment followed by relaxation. Alignment will be considered complete once the target placement is obtained. Working through the exercise will help you understand basic use of the Alignme app. This will prepare you to carry out array alignment in more advanced tutorials, as well as in your own applications. See the PowerPoint presentation and its associated M-file script for details. Guided exercises for generating a pad file and for creating a subject-specific finite element head model are also available. Additional information may be found in the resources listed here. Feel free to contact the development team with questions or post them in the comment section below. Thank you for your interest in NeuroDOT.